students, so welcome to the 8th lecture. We are now going to move to another topic. In the last section, which was I think 4 lectures at least, we were on a mission to do what? Embrace uncertainty, right? So we shaked this, or we shook this concept of a variable which was always taking similar values, or we changed the concept of an event which was deterministic, a process which was deterministic, and we included uncertainty, right? And the source of uncertainty, of course, we've been discussing that, so we skip that. But we decided, okay, let's bring in the uncertainty into these, and when we did that, we then collected whatever information we have within that uncertainty range, yeah, into various measures. The probability measure we discussed. Okay, event A or variable X is random, fine. Can I still assign some likelihood to it, some measure of chance of its happening? And that was the P, big P for us, yeah. Then we tried to collect those big P's into some sort of functions. Yes, what were those functions? Distribution functions, density functions, cumulative, joint, yeah. All of them were doing what? Collecting this big P one way or the other. Sometimes in the range, sometimes sum of those, integral, whatever. So we were doing that. Now, having done that in a general way, we haven't actually talked about the examples. Just uniform we have discussed a little bit. That will come later. But before that, I want to continue on this path and say, okay, we embraced uncertainty, we included or collected the whatever information within the uncertainty we had, we collected them in these distribution density functions. But then we kind of ended up with too much information. We will see that from practical point of view, density function, distribution functions are nice to write out and that all that, but it will turn out that that is just too much information. And now the next section or module that we will do maybe on next 2 or 3 lectures probably is to then say, okay, can we extract some useful parameters from the distributions, yeah, that can be proxy for or can encapsulate or represent. Representation ka idea, you know, yeah. You cannot I think Switzerland does this, but in most countries that are not dictatorships or kingdoms, what you have is you elect people, they sit in some parliament or senate, and they debate over everything. Imagine having all of Pakistan debating over everything. हो जाएगा काम मुश्किल है. In I think in Switzerland they have this, but the population is limited. They know how to go. So I think they do it like apart from daily running of business, almost everything, if I'm not mistaken, it's Switzerland, is done through voting, like referendum. Okay, so they go back to the people on everything, yeah, or at least all the major policies here. In our case, we elect for 5 years. At least we think we do that. Anyway, so 5 साल किसने पूरे किए? एक दफा हुए. I don't know. Okay, I think same prime minister hasn't done it. Yeah, with same party has done it, thankfully, but same prime minister has never done it. I think. Anyway. So representation, yeah, too much going on. How can we take the representation of that and then use that representation as a proxy for the whole thing to make some decisions, design whatever we wanted to do. So I like this, normally I like to give this information. Let's say you are giving an interview, yeah, and somebody asks, okay, how was your performance in undergraduate? The interviewer asks you. You say, okay, you know, I started out with a GPA of this much, then I improved a little bit, then it was like that, then I just couldn't perform so well in the fourth semester, then I get really well in the fifth. By the eighth semester, that guy will decide not to hire you. Too much information. Yes, there is a. What do you do then, other than this? You give them your CGPA. Yeah. So you say, yeah, I performed well. My CGPA was 3.3. Yeah. Now that CGPA somehow represents some sort of summarized, or let's say representative information of that 3.2 CGPA. Yeah. So why did you do that? The cumulative. Yeah. Because again, there is something like a too much information. Well, if you tell me there is a random variable, it can take values from 0 to 1 over some distribution function with some PDF and density function, and now you started me at 0.0001 it's this, 0.0002 it's this, and if it's continuous, imagine we'll go crazy, yeah? Or even using some functions can be hard. So here you do that already. You summarize, or you bring in a parameter that captures some effect, overall effect. Yes. So in our case, those effects. So we have looked at PDF density function. We have looked at cumulative. We have looked at mass functions. Yeah. We want to have some, well, this is already covered here, so I'll not do that. It's redundant. So these are the main two for us from here on. We want to take out some parameters, some representative values, like here CGPA. Yeah. So we can work with them instead of the whole thing. Yeah, you can go back to that if you have that full thing available and work with it, but for most practical purposes we don't go there too much. Yeah, we do decide some function on it. Is it normal, uniform, Poisson, whatever, that we do decide or try to decide. But other than that, actually there are cases where we don't even bother for that. We just go for mean variance based on data we have collected. Yeah. Then these things, one way is to go for what we call moments. Okay, and these are basically some representative values, and in these lectures now we will look at these. What I want you to have after, at the end of this group of lectures, the module, is to have a very clear understanding of what each of these means. Not just for one variable. For one variable, random variable, you know, mean, variance. But then, like we did before, we go from 1 to 2. So what can we bring in? Covariance, for example, right? So correlation, covariance, and then we'll also see, okay, what's beyond variance. Yeah. We won't do too much of that, but just to give you a teaser for that, you know it, yeah. It's skewness and kurtosis. Yeah? Third moment, fourth moment. But what are they? At least the first two, what are they? For single variable, for two variables, for more than two, what are they? How do they represent, or what part of it do they represent? Yes, and how can we use them? Yeah. So I would like you to have a very clear understanding of this thing by the end of these lectures, and we've already started with the motivation. Yeah. It's not like we say, okay, we did PDF, so the natural thing is let's go to moments. Why? What's going on? Yeah. So I'm not saying that they were developed exactly for this need, but for all practical purposes, this is, for me, this is more like applied maths course. Yeah. For practical purposes, this is what really happens. These are going to represent the big guy. Yeah. Okay. So our favorite moment, of course, is the mean. Yeah. और क्या नाम है उसका? कितने नाम हैं? Goes by many names.
Mean, average.
Yes.
expectation,
Expected value. What else?
and I have weighted average, we could say. It's kind of some average.
Well, that's a variation of the average, so still average, yeah. First moment.
First moment.
चौथा नाम. Yeah. So at least you know four names. बड़ी कोई बड़ी special चीज़ है जिसके चार नाम है माशा. Right? Mean, average, expected value, first moment. Yeah. Okay. So since this is a graduate
The
course,
moments is a representation of random variables or the probability on that random variable.
it's the representation or some summarized information parameter from the density or distribution of the n, which is of course the probability.
Okay.
Yeah. But by one more hop, it is representing the random variable. Yeah. So these guys are of course representing some random variable. Yes. And this is, we say, too much representation, too much information. Yeah. So we extract some 2 or 3 points from these are all the points here in it. So we take some first moment, second moment, third moment. Yeah. So they stand in for this guy. Yeah. These moments, and this distribution or density stands in for the
This
random.
moment.
So of course by proxy it is connected. Yeah, of course. So um, what I want you to know is that what I want you to motivate here is why not stop here and why go even further. That's what I was saying. From this example you agree. Yeah. So there is a lot of information in the density functions and we want to come back now. This is a graduate course, so you have had some probability already, so that's why I can ask you what is mean value. About the time. We can convert it into a quiz.
Um,
Average of random variables.
Average, so that's another name. Yeah.
It's kind of expectations of data, expected value. You could say on the weighted average.
How is it weighted?
It's weighted like that. If we have some data, then how much each one will contribute in the data. So we will all collect together, and we make one representation of it. Okay, this one have high contribution, and second one has a low contribution.
So what do you mean by contribution in this case?
Contribution we could say the probability. So how much total? It is actually the that one which approaches to all other. That is very close to all others. So that we could say that is the average. Or
Close
mean.
to all others.
Yes, that is.
Okay. So it's like let's say that we were talking about a line and an interval. Then you try to find a point which is close to all other points. Is that it? Or
Close to all others, or the representator of all others. Like just like a.
yeah, you're getting close.
Yes, just like
Yeah.
a CR in the class.
Mhm.
So that is, we can say, that is approachable to all other, and that is one very close to the representator of the class. That's
Yeah, but in our case, there is not one representative. There are others also, right? So then we'll have to see how are they different. How is variance, skewness, kurtosis different? Yeah. Okay, good. I think we can build on that. So firstly, let me just ask another question related to it. Is it the most probable value of the random variable x, the most frequently occurring value?
may or may not be.
Okay, so no.
Yeah.
Yeah. You say yes.
In case of
आप
finite,
क्या
it is
कहेंगे?
probable. Sir,
No.
Sir, in case of finite, it is probable. In
Uh-huh.
case of infinite, it is.
Yeah, but I'm saying is the mean value the most probable value of the random variable? Is it or no?
No.
No, right? So we know there are distributions where mean value is the most probable, but in general, it's not the case. In fact, the mean value may not be possible. Yeah, can you think of an example where the mean value is not even possible?
Just like simple 1, 2, 3 up to 6 divided by 6, so it's
Yeah, so if you roll a die,
3.6. Yes, sir.
each one has probability
1 by 6.
1 by 6. 1, 2, 3, 4, 5, 6. The mean value is
3.5.
0.5. It doesn't even occur, it's impossible in our experiment, but this is the representative value. Yeah, so definitely it's not the most probable value. Even here, let's say there is some continuous distribution going on for long here, then this is the most probable value, but it's not the mean value. Most probable means among these values, which one has the highest. Remember, now I've drawn it continuous. So this one is PMF, that is PDF, density. And as you see density, always remember these heights are relative likelihoods. Here the heights are actual probabilities. Yeah. So here, if the point is at the highest, it's saying I am most likely relatively compared to others, not all the others put together. I mean, more likely with respect to any one other. Yeah, but uh, most likely you can guess that this is not the mean value for this guy. Yeah, but for a fish distribution, you know, very nice one, Gaussian. Yeah, that's where the most probable value is the mean value. Yeah, but we'll come to that. So okay, we take that out now. The mean value is not the most probable value in general. Yeah, that is not the definition. Okay. And it's not even, as I said, it's not even possible. So any idea why we call it moments, these things, moment? Moment के क्या क्या मानी होते हैं? सुनते आ रहे ना, you have heard the word moment. Yeah. So did you ever think about why moment? क्या मकसद है?
Just to summarize data of in 1 minute or one time. So that's about it.
Yeah, it's not that moment. But but it's interesting. I'll give you you know, there are techniques of learning. I'll send you. I've written some articles. They are in Urdu. Uh, when I wrote them, I thought that people in Pakistan would find them more useful. Now people tell me to write that in English. So, anyway, I'll send you those. There are techniques of learning efficiently. Okay? One of those techniques that I've always found useful is, um, do you know इश्तिकाक का पता है आपको? उर्दू में इश्तिकाक क्या होता है?
इस्तेहकाक
नहीं नहीं, वो नहीं, वो तो हाँ, इश्तिकाक नहीं पता. ओके, मुश्तक का पता है उर्दू ग्रामर में क्या? निकल, मुश्तक है उससे. इश्तिकाक in Urdu is etymology. Etymology means finding the roots of words. Okay, if you make your habit to find roots of words, you will learn so much. When you go into roots of words, you see so many connections. Now, if you come across a word one time, okay, maybe you don't have to check it. But if you come across it again and you realize, okay, this word is a bit common in my work or something, just go to Google, write etymology space moments. Yeah, or etymology space this thing. Yeah. So it will start showing you the roots of those. Now in our case, this moment, when you come across it again or a couple of times, make it your habit for all these things, daily life maybe. And this is one of the key. There are other points of being an efficient learner. Yeah. So in what I've written, I've collected I think 6. I'll send you that small write-up. Yeah. It's a short booklet kind of, just PDF I'll send you. Yeah? It's written in an informal tone, but I can tell you this one first. Etymology. Yeah, going to the roots of words. Okay, this helps the learning process quite a lot. Okay, so moments. No, that's not the time. What other moment do you know? कॉलेज में कोई पढ़ी फिजिक्स में? Moment of force.
Moment of force.
वही ना, ये वो है. Okay, how is it? What is वो यहाँ क्या कर रहा है? Right. So let's see that. So by today you will know ये किधर से आ गया. How does it connect there? And how does it, as you said, the uh, overall contribution of, or you said something like that. You will see that thing showing up here in some form. Okay, so first I will say this, to summarize firstly the actual answer, then I will come to the moment thing and all that. I can write the mean as two ways. We will also see by the end of the lecture what's the difference between mean and average. They're not the same. Okay, although we could use it, but for a common person, when you ask them what's average, they have a very specialized case of mean in their mind. We will see that later. Yeah. So mean, expected value, first moment are exactly same thing. Average is a special case of them. Okay. Sometimes we just allow it, okay, average, but actually it's a special case. What is that special case? कभी सोचा है? नहीं? So we will come to that. Okay. So I'm going to say that mean for me has two, I can write it in two ways. I can relate it to the distribution, as you said, representation, and I'll say it's the center of mass. Oh no. चलो. Of the distribution. याद है moments वगैरह, center of mass निकालते थे? Yeah. Okay. This links to the PDF, yeah, or the PMF. And second definition I would like to put here is the expected worth of random variable. Let's say some x for single. Now I'll explain both of these, yeah, and we will see what do we mean by center of mass and those things. Okay, let's start with this thing. Let's say you have a PDF, yeah. Let's say the PDF looks like this, the normal one. Yeah. Now see, imagine this is a beam, yeah, of wood or metal or whatever, like you had in physics, and this is some lump on it, clay hair, something. And you have to put a wedge under it so that it balances. Scale bun gaya na. If you put the wedge here, does it balance? If you put it here, क्या होगा? इस तरफ गिर, tilted. Where should you put the wedge in this case? It should be here. Yeah. Okay. Let's say the distribution is a bit skewed, so it's a bit heavy on the this tail on this side. Yeah. Should I put the wedge here? Could be, but it seems from this diagram it would most likely, if I put the wedge on the most probable value, the value most likely relative to others, it's probably going to tilt this way. Yeah. So I have to shift the wedge most likely a bit to the right. Yes. But how much to the right? Firstly, let me tell you this. The place where you have to put this wedge, these are values of x here, yeah. So x, values of the let's say x is distributed as fx x, then the values that this x takes are here, and fxx is the vertical axis, yeah, like that. So the value of x where you have to put the wedge to make this thing balanced is the center of mass, and that value is the mean value. Okay, where do moments come in? Very simple. Let's see for the discrete case, and it will be easier for you to see. When you studied moments and those things, remember what they used to do? Hang weights here, right? Wasn't that either?
Yes, sir.
And then they say, okay, put a wedge here, and this distance was called what? Moment arm,
Yes.
right? And then there was the force, and distance times the force, yes, and distance times the force. Then these are in one direction, yeah, then the opposite direction. That all of these with their directions included as plus, you could get all this plus and this minus, or this minus and this plus. All of these, if this wedge is actually at the center of mass, what should their product sum be? 0.
Zero is.
All of them.
Net force will
The
be-
left should be equal to the right, or another way of saying is that if I bring that to here and sum them all with the sign included, then if I am actually at the center of mass, if I am not, then their sum, this times this, yes,
sir.
the moment arms times the force, plus the moment arms of this times the force it applies, plus all of these, yeah, all 4 of these should equal 0. Yeah. So in the continuous case, if you remember, you used to make small like pieces, and then imagine, okay, this piece is here, and that led you to integration kind of results, but it was the same kind of thing. Yeah. So this thing, you are finding the center of mass of the distribution, okay, and you understand, okay, the distance represents how far this, let's say this is the mean now, and so the distance represents how far this point is from the mean. That will be the moment arm. Yeah, but what is the weight here? This was actual weight, yeah, in newtons for the real physical system. For us, what is the weight? As you said, in some way, it's the likelihood, the probability. Yeah? So if one variable is more likely, it is putting more weight. Yeah? If a point is less likely, it is throwing less weight. Yeah? And with that, you can, for the discrete case, you can already start to see. Now try this little bit with the, yeah, I don't have good marker, it seems. Oh. So 1, 2, 3, 4, 5, 6. You roll a die, fair die, so each one has weight 1 by 6. Yeah. So imagine these as those weights that you have hanged. Each of these, I am just going to draw it as an arrow just to emphasize. Yeah. Each of these is applying its weight on this beam. Yeah. How much weight is it able to apply? 1 by 6, 1 by 6, 1 by 6, 1 by 6. Yeah. Now you have already told me what's the mean, 3.5. But now you can counter check. Yeah. If you put the mean anywhere else, the weights won't balance. You will not be at the center of mass. Yeah. But if you place it here, then each one's distance from whatever point you choose, let's say we call it mu x, each one's distance from it multiplied by the weight it's able to apply. Multiply, that is the value times its likelihood, or its probability of happening. That is the weight. So in terms of distributions, it's the center of mass of this thing. We will also do it more mathematically precisely, how to then, here we intuitively know it's here. Yeah, But what if this was 1 by 6, this was 1 by 8, this was 1 by 9, 1 by 15, 1 by 20, and 1 minus whatever, so it all sums to 1. Then if I give you घूम जाएगा सार थोड़ी देर, where should you put it? So we need a general formula. Yes, we will derive that general formula. Yeah, and that will be the familiar formula of the mean. But this time it won't be just given to you. Yeah, you will have developed it based on your understanding. That is the center of mass. Now, center of mass distribution is nice to define mean and everything, but still it doesn't give a real life feeling for what is it saying. What is 3.5 in this case? Yeah. For that, I like to go to the second definition or second interpretation, which directly links to the random variable. Yeah, it is the expected worth of the random. What is that? Okay, let's see. Let's say we play a game. Before that, can one of you go to Shafiq Saab and ask him for black and blue only? Red doesn't appear good on the screen.
I was considering that's a game.
Oh no, so ज़्यादा ही advanced game. But please, I will send you those write-up. Try to read it and see if you can adopt those methods. There is something. There is learning, and there is effective learning. Yeah. Before that, there is some natural capacity or natural. Now your natural capacity for learning is debatable. Some people say there's nothing like that. It's just training and everything. Okay, even if it is real, it's not something you can do anything about. Yeah, if you say your natural learning ability is good, okay. If it's a little bit below good, you cannot sit and cry over it. Yeah, in both cases, it's not in your hands. What's in your hand is efficient learning methods. Now, people who adopt, either they adopt these naturally, okay, fine, but we don't have to wait for things to happen naturally to us. Yeah, smart people, they can also learn from experiences or of others and adopt efficient learning methods. I mentioned one about etymology. Notice just the trying to understand moment, the word moment. Why are we using this here? Just that leads to this whole thing, and actually that will lead to the formula of this thing eventually of mu x. Yeah, so but if we don't ask, we'll just say yeah, it's x fx summation or integral. Yeah, so thank you. नहीं है ना, इन सारों को रिटायर कर देते हैं. So let's play a game, and I say I'm going to now come to this interpretation, then we'll come back to this one to actually derive the formula of the mean. Formula of the mean क्या है?
Summation of the elements divided.
X into f of x, summation of x into p of x of x. That is for discrete case.
Yeah, and for
And
continuous?
integration of x f of x.
Yeah, but where did the formula come from? Today we will derive it from here. Exactly, निकल के आपके सामने आएगा वो. From the moments, from the center of mass. Okay, but before that, I want to cover this thing because I think it's also important. For me, center of mass has, I will explain it. It has meaning, but this one is more, let's say, from a real daily life understanding, the expected worth of random variable. So we're playing a game. I say we have a fair coin, and we toss it. Every time we get heads, yeah, I give you 100 rupees. Yeah, and every time we get tails, you give me 100 rupees. We have converted from random event to random variable. Remember I was saying mapping? How do you map? We said there are many ways. Already now you have mapping shuru ho gaya na?
Yes.
So it will depend on what you want to define. Let's say this is the mapping, yeah. So the coin is fair. That means it has only two possibilities, and probability of first possibility, that is, let's call it head, is equal to the probability of second possibility. Each is 0.5. Heads and tails come with equal probability. Okay. So here I'm going to call this x1, this one x2. Remember the mapped value, yeah, from these three. Right. Now, how much do you expect to win or lose if we play this, let's say, several times? Before the game, how much, कितने rupees में बताना है, chances नहीं. How much, not what's the likelihood. What is the expected worth of this game?
Zero.
Zero है ना? Yes. क्योंकि क्या होगा? If it's a fair coin, each one will appear with equal probability, so each one's chances of happening are same. Now once one of them happens, how much it can give you or take away is also same. One of them takes away, one gives you, but the amount, the amount they can give you is the same. So firstly, how much do you expect to win or lose per play, or overall, or expected worth? Can I say that the expected worth of this game or this variable x for me is, I can win 100 rupees and their chances are 0.5, or plus, remember for us, or I could lose 100 rupees and their chances are 0.5. What's the expected worth? Zero. You intuitively already mentioned it, and you will see the formula you wrote for discrete expectation. Yeah, it's already showing up, but we will actually derive it from moments also. Yeah. So yeah, this game is really not worth playing. कोई मजा नहीं है इसमें. Yeah. So let's. In this case, I'm going to just to get things going towards the formula also. Can I write it like this? ये लिख सकते हैं ना, यही लिखा ना हमने, in terms of the variables, and we will define it as the expected value of x. I'm not defining the general case, just here, let's say. So this is the expected worth of x, 0. Yeah, क्योंकि win some, lose some. So logically, what really happens if you imagine it? How did we get to this? If you play 1,000 times, yeah, what's going to happen? Roughly 500 times you will have 100, and 500 times you will have minus 100. Not in this order, of course. It will be mixed up. But for my own convenience, I am writing it like this. So in each play, basically, overall, in the 1,000 plays, what will happen? Each time these will cancel out. Yeah, they will start cancelling out, and you will be left with 0. Another way of looking at it is that overall, they all cancel out. Yeah, and you get 0. Okay.
Expectation can be negative also.
It's not the expectation. Expectation can be negative. Yes. Yes. Depending on the
Situation of problem.
the range where you. We will see that also. Now let's make this more interesting. Yeah. let's say, so in terms of, by the way, in terms of center of mass also, this one, at least this particular case, how can we draw it? If I want to draw the probability mass function of this, yeah, so how many possibilities it has? Two. X can have value minus 100 or 100. Yes, so where should the wedge be to keep it balanced? This is the mean point. Yes, so x1, x2. Yes, so what do we get? What is this distance?
ux minus omega x minus x1.
Mu x, yeah.
Minus
100.
x minus.
So also we have to, this is x1, x2 minus 100, and we have to bring in what? The weight they apply, yeah? This was P x x1, and here it's P x x2. Yes, and in this case you can easily see that this distance, this thing, which is including the sign here, x1, the moment of this force here. Yeah, what is that moment of force? The moment arm times the actual force. So x1 p x1, if it is actually the center of mass, it should be equal to, let's see, where is that?
x2p of x2.
Yeah, x2 p, but we also need to bring in the mean. So I will come to that, but for now we know, of course, it should be equal to x2 of p x2 if we are putting it over there. So we will see that if we assume we have put it at 0, so this should be fine. We'll generalize it, but let's come to the bad thing. Let's make things more interesting here. I say every time we play, every time a head comes, I give you 100 rupees, and every time there is a tails, you give me 1000 rupees. Okay. Now in this situation, firstly, should you play this game? Yes or no?
Yes.
You should play this game, yeah? And let's say let me change the odds here. Now what's happening? Every time there is a head, I give you 1000 rupees. Yes, and every time there is a tail, I take from you 100 rupees. Should you play this?
No.
This one. So I give you 1000 for heads, and I take from you tail 100 for tails. Yeah. So then, for your point of view, you should play this game because you expect to gain. Okay. How much do you expect to gain or lose per play? पिछले केस में तो 0 था ना. What is the worth of this game for per play? Yeah, हर दफ़ा जब आप एक दफ़ा खेलेंगे, ये तो probability की बात हो रही है. Actual won't follow exactly, but in long run it will come. So what do you say?
Expected value is
So we will calculate its mean.
Hmm. Right, and that will lead you to
And that will make our.
this has changed, yeah?
Yes, sir.
So what has it changed to now? For your case, again, now you expect to win 1000 with the chance of 0.5. Yeah, although the chance of each one occurring is still the same, but once one of them occurs, its worth is much higher. ये वो जो force उसने लगानी है, yeah. So or this would be the force and this is the moment arm. So you know, longer the moment arm, bigger the contribution, right? You can increase the weight to increase the contribution or increase the moment arm. Yeah. Here the two are applying same weight, but one of them has a huge moment arm, 1000 का है उसमें. So if you calculate this, क्या आता है ये? What is the worth per play?
45 आ रहे हैं.
45 क्या? मेरे पास 450 लिखा हुआ है, देख लो दोबारा.
450.
सिर्फ 45 रुपये चाहिए. 450, हाँ. So this 450 now, does it make sense to you now what the expected value in this particular situation mean? Yeah. So
The worth is
it means the what amount you expect to win or lose in this particular scenario. Yeah. So the expected worth, expected value of that random variable. Now, how much should you win in let's say, should you expect to win if you play this game 8 times?
8 times.
450 was your expected per play, है ना? So if you played 8 times, assuming each play is independent of the other, कोई effect नहीं है उसमें तो.
Then we'll take average of all these expected values.
Yeah, you could do that, or you could just multiply by. So you expect to win 450 per play, 8 plays. Yeah, as long as they are independent, so you will win 3,600. So of course you should want to play this for a very long time. Yeah, and it will be dumb of me to play this game with you because I keep losing. Yeah, on average. Per play I lose 450 on average. Yeah, and what is happening in terms of this thing, let's say we play 1,000 times, let's say. Or yeah, let's say we play a lot for the 8 times. Let's say we play 8 times. So what should we expect to see? But based on the chances, yeah. In reality, you have to play much more to get there. But based on the chances, 1,000 was 50% chances of 1,000, and then 50% chances of minus 100. Yeah. So per play, pair of plays. These are your 8 games. Yes. And if you notice, you see this and this and this. This is 900 times 4. As here.
yes.
So that is 3,600. Yeah. So that also pans out. Okay. This is what we again expect. I could be extremely lucky. Okay. And it could happen that this 8 of these are minus 100, minus 100, minus 100, and you end up paying me 800 rupees. I could be extremely lucky, yeah. But expected value, of course, is this much. Yeah, from all logical purposes. And normally as things go longer, then it becomes more clear. There was a professor of teaching random processes in the US. What she used to do is ask students in the first lecture to take a sheet of paper in their homework at home and write numbers from 0 to 9. So 0, 1, 3, whatever they want to write on this sheet of paper, and write those like around 1,000 of them, or fill the sheet. So like you are writing 0, 5, 6, 8, 9, 3, 2, 1, 6, 3, 5, 4. and then students would bring to her in the next lecture, and she could look at it and tell them that so if I remember correctly, they had two options, either to write it by themselves or use a computer to generate those 1,000 and then write them with their hand. In both cases, she could look at the sheets, and in most cases, she could tell if this was written by a human or a computer. Okay. And her trick was that when humans were writing, they were trying to avoid writing same number 3 times, like 0, 1, 1, 1, 1. They were thinking, since I'm writing random numbers, so I shouldn't repeat. But reality is different. When you actually run on a computer, you can get long strings of the same number because they are all probable. It's not an issue. So she could find those strings and say, okay, this was generated by a machine, whereas a human was deliberately avoiding repeating. Yeah. So this is an interesting result here also. Although this is the expected worth, and if we write it, we will try to write them equally. But it can happen that they are all minus 100. It is possible, and it does happen. So anyway,
That's not his expectation. That's all his expectation.
that's the expectation. Yeah, expectation. So now let's connect this example of the 1,000 and to get a more interesting definition or the formulation for the mean value. Yeah. So now in our case here, if we go to this case, you had minus 100, yes, and 1,000, yes, okay, and the weight they were applying was 1 by 2 and 1 by 2. 0 is somewhere here, yes. By your common sense, you know this is not the center of mass. It's a bit to the right or the left, and you calculated it. But let's say you didn't have that formula, and you had to answer this question. Then you will, as mathematicians do, just put it somewhere, draw it, and give it a name. Yeah, box, question mark. Let's call it mu x for now. We haven't calculated it. Okay, for all we have in mind is where do I put this for this particular case for this to be balanced. Yeah. Now let's see. In this case, if I can say, what is this distance? Remember these values, if we are calling these x1 and x2, and this is p of x1 and this is p of x2. Right, so what is this value? This moment arm, how much is it?
X2 minus P of X2.
X2 minus,
Absolute
yeah?
distance.
We don't want we want to allow the sign also, because remember in moments you counterclockwise is positive or they are opposite, yeah? So same here. What about this one? What is this value?
X1 minus
X1 minus mu x, and of course this will turn out to be a negative value, which we want to allow because they are on opposite sides of this wedge of the fulcrum, so we allow the negative and positive signs. Okay, then now this thing, moment arm x1 minus mu x times the force or weight it's able to apply is p x1. Agreed? It should be equal if this is truly, we don't know yet, yeah, but we're saying if it is truly the center of mass, then it should be equal to the minus of this, right, because they are opposites. So I'll skip that and just write it, plus this thing p x2 equals 0. This is another way of saying that same thing for balance. From here, can you extract mu x? Try करें. We were looking for mu x, right? We just wrote the condition it has to meet. Mu x should be a point such that this moment arm times the probability that applying the weight thing. What do you get? What formula do you get for mu x?
So it's x1 p of x1 plus x2 p of x2 over p of x1 plus p of x2.
Right. Yeah. That's not the formula of mean, is it? We can cheat. We know actually. Yeah. Let's. So what are you missing? इसलिए मैं आपसे करवा रहा हूँ. I want you to get there. You know the formula of mean. Yeah. We're cheating, so we know the formula of mean. This is not it. Yeah. What's going on? You know, the human mind works better when something goes wrong. So many professors, they deliberately design examples and problems where their students are getting the wrong answer again and again. So it kind of challenges you. But anyway, here it doesn't seem to be coming out to what we wanted. So क्या हुआ? गलत हो गई? Is it wrong? Did I make a mistake? फिर अच्छा आपने क्या लिखवाया? लिखवाया मुझे क्या है आपका म्यू एक्स
x1 p of x1 plus x2 p of x2 divided by p of x1 plus p of x2.
Yeah. So can you see what's going on?
अगर नीचे वहाँ पे 1 हो जाए then
अगर क्यों होगा नहीं 1? It will always be 1. Even in this case it's 1. 0.5 plus 0.5. But in general, let's say there were 10 of these x's. Yeah. So essentially we were saying, let's say xk of these, let's say mu x p xk, we were saying this is 0. This is what we're saying for the 2 case. What you ended up with is essentially saying that mu x is summation this thing xk p xk divided by summation p xk. Yes, but of course what's the total sum of probability?
1.
It will always be, not just this example. Here you could put 0.5, 0.5, I've given you the values, yeah, but not just here, everywhere, always, unless you haven't included everything. If you haven't included everything, then your diagram is wrong. You cannot find the center of mass of that distribution. You skipped some values. Yeah, you skip a value and then find it here, you're wrong. Yeah, so you have to cover everything. If you cover everything, this will always be 1. Yeah, this is the formula for the expected value. Okay, and it has everything to do with the moment of force जो आप पढ़ते हैं. Yeah, what is this saying? It's saying what is the amount this guy is going to contribute. Okay, Like here, in this case, for example, if we write it, now we just look at it here like this, saying, okay, the amount it's going to contribute is 100, yeah, minus 100 here, 100 times what are the chances of that happening? Yeah, if the amount is large or the chances are large, then its contribution will be higher. Yeah, it could be that the chances of one of these happening, let's say this is minus 10, and the chances of this are, let's say, 2 by 3,
Yes.
more than the other. Yeah, now it's not clear. Yeah, this has higher chances, but should we think that you will lose overall? Not clear, because yeah, the chances are very high, they could even be 90%. But just because, okay, you win 90% of the time, but what do you win? What do you get from me? Just um, minus was losing for you. Okay, so how much do you lose every time? You just lose 10 rupees every time. Yeah, or it could be the other way. So it could be that you gain 90% of the time. Sorry, it's let's make it like this. You gain just 5% of the time you win. Okay, it's some sort of, it's not just coin, some other experiment where
Playing cricket
95% and 5%.
Playing a cricket match is very much strong team.
Yeah.
Like,
So here you may think, oh, every time we play it, for me winning is 1000 and losing is just minus 1000. Yeah, okay, but notice, out of 100 plays only 5 times you will win. Yes, whereas 95 times you will lose. So you still have to calculate. It seems it is still in your favor, by the way. Yeah, because if you win out of 100 you win 95, so this is 95,000. Sorry, 5,000. 5 times. And this is 950. You lose. Still in your favor. Yeah, but you can understand that a large value, let's say, even if we make it even much smaller chances, 0.1 or 1% chances, then a large value alone is not enough. Why? Yeah, you say you lottery है आपकी, billion rupees निकल सकते हैं. Yeah, huge value, billion rupees is there. फिर क्या हो जाता है अचानक?
chances बहुत कम होते हैं.
कितना सा तो वो force ही नहीं लगा रहा. Yeah, it's not applying any force, it's not adding any, मतलब if it happens it has huge worth, but what are the chances of it happening? That's why every time this is very important. This is the it could still happen, फिर तो हमारे न्यारे हो गए ना. Yeah, but before the actual play or actual lottery is drawn, it is what the expected value is. Okay, so are we clear on that? So mean is the center of mass or the expected worth of, and by center of mass already you include moment. So this is the first moment of our distribution, and often it helps us for especially the more common Gaussian case. It helps us locate where the distribution actually is. So if mu x is 10, if it's Gaussian, mu x is 10, it's here. If mu x is 50, then the Gaussian distribution is here. So sometimes we say it's the location parameter. Doesn't always fully mean that way, because distribution can come in many shapes and sizes, but anyway, sometimes people like to call it for simplicity purposes. So I will not go into the second moment today, but I have a quick question for you before we end. What is the mean or expected value of a constant?
Expectation 0.
Okay, what rule are you applying? What's the expected value of a constant? C is a constant. Let's say C is a constant. It's not random.
Yes.
Yeah, C, some constant. What is the expected value of C? quickly. Okay, 0.
0.
Try to apply now quickly before we go. Apply this thing. Draw for C.
C आएगा.
C आएगा. Expected value of a constant is the constant itself.
Because हर time ही वो है कि probability 1 है आने की. Every time it's happening.
Right. So that is the expected worth. But in terms of center of mass, try it. Draw करें. I also want you to see this thing happening for this case. क्या होगा? किधर रखेंगे wedge? As your colleague said, of course, this is the value is C, and the chances of this value happening are 100%. So it is C. That's the expected worth formula. Now I want you to do it with this thing. So नजर आ गया क्या हो रहा है? कैसे होगा ड्रॉ? हो रहा है या
एक ही पॉइंट है.
एक ही पॉइंट है? उसकी क्या है उसके ऊपर?
कुछ
नहीं, ये जो पॉइंट कहाँ है? व्हाट्स द पॉइंट?
सर यहाँ कांस्टेंट कहीं भी
C.
सेंटर.
Yeah?
Yes.
ये पॉइंट है. ओके. What is the probability worth? यहाँ पे क्या है वर्थ? P की
0
0 0 0. यहाँ क्या है?
1.
1. तो इस constant.
1 is 1. अब वेज कहाँ रखेंगे? ये वेज है ना, where you have the mu x. Where do you put it? If you put it here, falls to the right. If you put it here, falls to the left. It has to be put exactly on C. So both ways you come to the conclusion it's not 0. आप variance से confuse कर रहे हैं. Right. So the variance of a constant is 0. We will come to that later. Okay. Right. So that's it for today. Thank you so much.